Welcome to this explainer. Today, we're going to completely demystify exactly how data travels across the internet, and more importantly, how networks are organized behind the scenes to prevent, well, massive traffic jams. Seriously, if you've ever stopped to wonder how billions of devices manage to communicate simultaneously without the whole system just collapsing into total chaos, you are in the exact right place. We are looking at the fundamental architecture of the internet today. Okay, let's take a quick look at today's agenda. We're going to cover 1. The role of IP addresses. 2. Local versus remote delivery. 3. The broadcast domain problem. 4. The subnetting solution. 5. Subnetting on octet boundaries. And finally, 6. Classless subnetting. All right, let's just jump right in. Section 1. The role of IP addresses. We absolutely have to start at the foundation here. How devices actually locate each other on a network in the first place.
So, every single device connected to a network needs a unique IP address to communicate. It's basically the core requirement for end-to-end transport at the network layer. Now, thankfully, DNS, the domain name system, automates the translation of these addresses. It brilliantly matches simple, recognizable names, like your favorite website URL, to the required numeric network address. That way, we can just use words instead of memorizing giant strings of numbers. But make no mistake, under the hood, those unique numbers are doing all the heavy lifting. Take a look at how a packet's journey is mapped out right here, from the original source straight across to the final destination. And what's really cool is that regardless of how many intermediary routers the data gets bounced through, those IP addresses in the packet header, they remain exactly the same. They guide the data like a compass, pointing directly to its target. Now, to really grasp how an IP address functions, you have to realize it's actually two addresses crammed into one. To make this relatable, think of the network portion, that's the leftmost part, like a zip code. It determines the general neighborhood a device lives in. Then you have the host portion, which makes up the remaining part of the address. That's like your specific house number within that neighborhood. So routers primarily care about the zip code to get the data to the right general area, and then the local switch uses the house number for that final delivery. All right, moving right along to Section 2, local versus remote delivery. Let's see how a host decides where to physically send its data once it actually has that IP address. A really important role of the network layer is directing packets. A host basically has three choices. 1, it can send data to itself for testing purposes, which typically uses the loopback interface at 127.0.0.1. 2, it can send data to a local host, meaning a neighbor that shares the exact same network address. Or 3, it can send data to a remote host, sitting on a completely different network. To make this forwarding decision, a host compares its own IPv4 address and subnet mask with the destinations. That simple math tells it if the target is local or remote. And you can see that forwarding decision in action right here. Take a look at the local bubble on the left side. If the calculation shows the destination is on the exact same network, the traffic just stays right there in the local bubble. But if the calculation reveals a remote destination, the host knows for sure it must push the packet to the router, its default gateway, so it can be sent across the wider network. It's a simple binary decision, but it's literally happening millions of times a second. Section 3, the broadcast domain problem. The crucial point here is understanding what goes horribly wrong when these local networks scale up too aggressively. So what actually happens when networks get way too big and form one massive broadcast domain? Well, it becomes a major headache for network administrators. When an entire network is just treated as a single unsegmented space, yeah, it is a recipe for serious congestion. Just imagine cramming 400 users into one massive broadcast domain. That means every single host is generating unchecked broadcasts across the entire space. Every single time a device shouts out to find a service, request an IP address, or resolve a local name, that message floods out to all 399 other devices. There are absolutely no stop signs and no boundaries. As you can guess, the negative effects here cascade quickly. Because every single device is forced to accept and process every broadcast packet at the hardware level, overall network performance just grinds to a complete crawl. The network gets heavily congested with traffic, and individual computer processors are forced to waste vital cycles discarding all this irrelevant broadcast noise instead of, actually running your applications. Which brings us to Section 4, the subnetting solution.
Fortunately, we can actually solve this massive traffic jam by implementing smaller network spaces called subnets. By segmenting the network, and you can do this physically by building floors or logically by organizational department, administrators drastically reduce overall traffic. For example, a broadcast generated in the accounting department just stays in the accounting department. And beyond just making things faster, this segmentation allows us to enforce strict security policies so we can choose exactly which subnets are even allowed to communicate with each other through the router. It's a real game changer. Section 5, Subnetting on Octet Boundaries. Let's take a look at the absolute easiest and most common way administrators draw these new network boundaries. Networks are most easily subnetted on octet boundaries. That means we split the network and host portions exactly at the 8, 16, or 24-bit marks in a standard 32-bit IPv4 address. You can see how moving from a /8 prefix down to a /24 drastically shrinks your host capacity per subnet. You go from over 16 million potential hosts in a single /8 broadcast domain down to a very manageable 254 hosts in a /24 network. The /24 boundary is incredibly popular, mostly because 254 hosts is usually the perfect size for a standard office or department. Now here's where it gets kind of cool. Let's look at the actual binary math under the hood. In the middle column, the 1s represent the network bits, the N's, and the 0s represent the host bits, the H's. This proves that subnets are created simply by borrowing host bits to become new network bits. The further to the right those 1s go, the more you are dividing up the space. Section 6, Classless Subnetting. But what if those clean octet boundaries at /8, /16, or /24 just don't fit our exact needs, and we need something much more precise? Well, classless subnetting allows us to borrow bits from literally any host bit position to create custom masks. We don't have to stop at /24. If we have a /24 block, we can slice it up even further. A /25 gives us 126 hosts. A /26 gives us 62. We can even create a highly customized mask like a /30, which leaves exactly 2 host bits. That gives us exactly 2 usable hosts, which happens to be the perfect, secure, and efficient size for a simple point-to-point router connection. And this right here perfectly illustrates the ultimate trade-off in all of network design. Look at the last 2 columns. As the prefix length increases from /25 to /30, the number of created subnets goes up from 2 to 64. But simultaneously, the number of hosts you can fit inside each of those subnets drops from 126 down to just 2. The more host bits you borrow, the more individual subnets you can define, but the fewer hosts you can put in each one. It is a perfect inverse relationship. So how does optimizing network traffic through subnetting fundamentally enable the speed, scalability, and security of the modern internet? I want you to really think about that as you consider how millions of devices manage to communicate globally every single second without the whole system instantly crashing from broadcast traffic. It's all built on this incredibly elegant foundation of IP addressing and strategic subnet segmentation. I really hope this explainer leaves you with a solid understanding of these core principles and maybe even leaves you eager to dive a little deeper into network architecture.